have you ever really stopped to think about how a computer actually does math? I mean, deep down, these things are just billions of tiny, tiny switches that are either on or off. So how do you get from a simple on-off switch to complex calculus? Well, that's what we're going to find out. Right. This is the big question, isn't it? How can a device that only gets on and off, or 1 and 0, do something as complex and logical as addition? It seems kind of impossible at first, but the answer is surprisingly clever, and it all starts with the smallest possible step you can imagine. Okay, so forget adding huge numbers for a moment. To really get this, we have to zoom way in. The entire foundation of how computers do math is built on one single task: adding two single binary digits, or bits, together. If we can solve that one little problem, we can scale it up to solve basically anything. So let's start our journey by building the most basic adding machine possible. Think of this as the first and most important Lego brick in our entire construction set. This first Lego brick is called a half adder. It's a really simple digital circuit. It takes in 2 bits, let's just call them A and B, and it spits out 2 answers, the sum of those bits and a potential carry bit. Now, why half? Well, its name comes from its one big limitation. It can't handle a carry coming in from a previous calculation, and we'll see why that's a big deal in a minute. This little table here lays out every single thing that can happen. The first 3 rows are pretty obvious, right? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. No problem. But look at that last row. This is where the magic happens. 1 plus 1. Now, in our normal decimal system, that's 2. In binary, the number 2 is written as 1, 0. So our little circuit outputs a sum of 0 and carries a 1 over to the next column. This is the absolute core concept of binary addition. And here's how we actually build it using logic gates. The sum is what you get from something called an XOR, or exclusive OR gate. It's 1 if A and or B is 1, but not if they're both 1. The carry? That's just an AND gate. It's only 1 if both A and B are 1. And that's it. With just those 2 gates, we've built our very first calculator. So our half adder is a great start, but remember that one big limitation? It's time to build on what we've learned and create something way more powerful. Just think about how you do math on paper, right? Like 15 plus 17. You add the 5 and the 7 and you get 12. You write down the 2 and you carry the 1 over to the next column. Our half adder, it can't do that. It has no way to accept that incoming 1. So we definitely need an upgrade. And the solution is this, the full adder. The key difference is right there in the definition. It adds 3 bits. It takes our 2 inputs, A and B, plus a third input called carry in. This is the piece of the puzzle we were missing. Now we can handle those chained calculations. And you want to know the best part? We don't even have to start from scratch. A full adder is literally just made of 2 of our half adders. We add A and B with the first one, then we take that result and add it to the carry in with the second one. A little OR gate at the end handles the final carry. This is just a perfect example of how digital circuits work. You build simple blocks, then you combine them to make more complex ones. Okay, now we can really start cooking. To add 2 4-bit numbers, we just chain 4 of our full adders together in a line. The carry out from the first adder becomes the carry in for the second, and so on. That carry signal literally ripples down the line from one adder to the next. This is how a computer actually adds numbers of any size, whether it's 4 bits or 64 bits. Now, this design is logically perfect. It will always, always give you the right answer. But in computing, being correct is only half the battle. You also have to be fast. And our neat little ripple carry design, it has a hidden weakness. The problem is that it's a waiting game. It's exactly like a line of dominoes. Each adder has to wait for the one before it to finish its calculation and pass along the carry bit. The third adder can't start until the second is done, which has to wait for the first. Now imagine a 64-bit number. That is a long line of dominoes to fall. This delay is called ripple carry delay, and in modern computers, it's just way too slow. So engineers came up with a much, much more clever solution. Instead of waiting for all those dominoes to fall one by one, they basically figured out a way to predict the future. What if, instead of calculating carries one at a time, we could build a special logic circuit that just looks at the 2 numbers we started with, A and B, and computes all of the carries at the exact same time? If we could pull that off, Every single full adder could do its job in parallel, and the whole calculation would be almost instantaneous. And that is exactly what a carry look-ahead adder does. It's a faster, way more complex circuit that sits alongside the main adders. Its only job is to figure out all those carries ahead of time, which just massively speeds up the entire operation. So how does it predict the future? Well, it analyzes each pair of bits for two simple conditions. First, will this pair of bits generate a carry all by itself? That only happens if both bits are a 1. It's a guaranteed carry. Second, will this pair of bits propagate a carry? This means if a carry comes in, will it pass it along to the next stage? By building a circuit that figures out these generate and propagate signals for every bit at once, it can see the whole picture and calculate all the final carries in a single step. You know, we focused entirely on addition, but the real beauty of all these circuits is that the same fundamental principles apply to all the other kinds of math, too. And check this out. This is just brilliant. The core logic for a full adder uses an XOR gate. Now, look at the logic for a full subtractor. It's almost identical. The underlying structure is so similar that engineers can use the same hardware to do both addition and subtraction, which is incredibly efficient. And it doesn't stop there. Even multiplication, which feels way more complex, is really just a process of repeated additions and shifting bits around. It's all handled by the same adder circuits we've been looking at. We don't need a whole new machine. We just use our existing Lego bricks in a smarter way. So let's zoom out one last time and see where these adders fit into the grand scheme of digital electronics. Everything we've talked about today, half adders, full adders, all of it, these are called combinational circuits. Their output at any given moment depends only on the inputs at that exact same moment. They have zero memory of the past. The other major category is sequential circuits. Their output depends on what's coming in now and what happened before. They have a feedback loop, and they form the basis of all computer memory. And that leaves us with a final thought. We've seen how a few simple AND and XOR gates can be combined to build circuits that do seriously complex math. It just goes to show you that in computing, everything is built from something simpler. So that leads to the next logical question. If these gates are the building blocks of calculation, what are the fundamental building blocks of memory?